Let's talk about indefinite integrals and the net change theorem. So far we've looked at definite integrals, or integrals that have limits of integration. In this section, we will look at indefinite integrals. Because of the relation given by the fundamental theorem of calculus between antiderivatives and integrals, we can say that the indefinite integral of f of x dx is equal to capital F of x, and that means that capital F prime of x is equal to f of x. Example 1 says, find the derivative of the following functions. So part A, we have f prime of x is equal to 16x cubed plus 7. And then for the minus 1, that's a constant, so that is the extent of our derivative. For part B, we have g prime of x is equal to 16x cubed plus 7, and then once again we have 15, and the derivative of a constant like 15 is 0, so here is g prime of x. And lastly, h prime of x is equal to 16x cubed plus 7, and the minus square root of 3, if we take the derivative of that, that's also equal to 0. So now example 2, we essentially want to relate the last three parts that we did, and we want to find the indefinite integral of 16x cubed plus 7. So because of all of the functions up above, when we found their derivative, that means that the integral of this thing is equal to 4x to the fourth power plus 7x, and then in order to make it so that we have a constant, I'm going to add plus c, and that is our final answer. This plus c has a special name. It is called the constant of integration. You want to make sure that you keep in mind that the definite integral is a number because it represents a net area, but an indefinite integral is a function or family of functions. So in the table below, we have some common indefinite integrals. You want to make sure that you have these formulas memorized. Example 3 says use the previous table to find the following indefinite integrals. So for part A, I am taking the indefinite integral of 8x to the fifth plus 7x plus 2 times dx, and this just is a polynomial, and so we would use the power rule in order to take the integral of this. So I'm going to keep my constant 8, and x, I'm going to increase the power by 1, and then divide by that new power, plus 7x, I'm going to increase the power by 1, divide by that new power, and then plus 2x, and if I raise this to the first power, it's kind of like I'm dividing by 1, and then I can't forget my constant of integration. I'm going to simplify my fractions if possible. So we have 4x to the sixth power over 3 plus 7x squared over 2 plus 2x plus c. And that is our final answer for part A. For part B, I'm going to rewrite my integral so that it's easier to use the power rule. So 1 over x to the fourth power is equivalent to x to the negative fourth power dx, like that. And here, if I want to use the power rule now, I'm going to add 1 to my power. So negative 4 plus 1 is negative 3. And then I'm going to divide by that new power. And I need to make sure to include my constant of integration. So that's the answer for part B. All right, so for part C, we're asked to find the indefinite integral of secant times the quantity secant plus tangent, and then minus 2 times e to the x dx. So here you have to be really careful because there's a parenthesis there and a parenthesis there, which means that we need to distribute in our secant x. So if I multiply secant into both of these terms, my new integral is going to become secant squared x plus secant of x times tangent of x minus 2 times e to the x. So notice that 2e to the x we're not having be multiplied with secant of x because it's not inside of the set of parentheses that we were looking at. From here, we learned previously about a property of integrals that would allow me to split this up into 3 separate indefinite integrals. So this is equal to the integral of secant squared x dx plus the integral of secant of x times tangent of x. And then in my next integral, I can factor out the minus 2 outside of my integral, and then I have e to the x dx. So how do we integrate each of these things? We want to look at the table that we saw at the beginning of this section. So the indefinite integral of secant squared x is tangent of x. The integral or the antiderivative of secant of x times tangent of x is secant of x. And then our natural exponential function is nice because its antiderivative and its derivative is itself. So I have minus 2 times e to the x, and then we want to make sure we include our constant of integration. So that concludes part C. Example 4 says to evaluate the indefinite integral of the square root of t plus t cubed plus 1 all over t squared dt. Now, what's going to make our life easier, and this is kind of similar when we were in Calculus 1, where we would make it so that when we were taking the derivative of something like this, we could use quotient rule, or to make our lives easier, we could make it so that it's no longer a fraction. So let's look at our indefinite integral. The square root of t is the same thing as t to the 1/2 power, and I'm going to split this up into 3 separate fractions. Okay, so now that we have 3 separate fractions, we can simplify these fractions, and if we wanted, we could separate this into 3 different integrals. So t to the 1/2 over t squared, that's going to give us t to the negative 3/2, because 1/2 minus 2 is negative 3/2, and then dt. Plus, I'm going to factor out the 2 outside of my integral, and we have t cubed over t squared, which is t dt. And then my last integral, I could bring that to the numerator by making the exponent negative, and so we have that. And for each of these, we can use the power rule for integrals. So I'm going to increase the power by 1. Negative 3/2 plus 1 is negative 1/2, and then I want to divide by negative 1/2, which is the same thing as multiplying by negative 2. In my next term, I have plus 2t squared over 2. And then in my next term, we increase the exponent by 1 and then divide by that new power, and we have our constant of integration. So let's clean this up a bit. This is the same thing as negative 2 over the square root of t, plus these 2's will divide out, and then minus 1 over t plus c. One thing that I like to emphasize to my students is if you write your t's and your plus signs the same, it can often confuse yourself or the reader. So I don't normally write my t's like this, but when I'm doing mathematics and I have a t variable, I make sure to include a tail so that I can differentiate it from a plus sign. And so that's something that I recommend to my students if you don't already do that. And that concludes example 4. This next theorem is called the net change theorem, and it says that the integral of a rate of change is the net change. In other words, the definite integral from a to b of capital F prime of x dx is equal to capital F of b minus capital F of a, where capital F prime of x is representing a rate of change. So let's look at some examples of that. The first one says, if the rate of growth of a population is dn dt, then the definite integral from t1 to t2 of dn dt times dt is equal to n of t2 minus n of t1, which is the net change in population during the time period from time 1 to time 2. The population increases when births happen and decreases when deaths occur. The net change takes into account both births and deaths. So if we end up calculating this and it ends up being a positive number, that means that there were more births than deaths. And if it ends up being a negative number, that means that there were more deaths than births. The second bullet point says, if an object moves along a straight line with position function s of t, then its velocity is v of t, which is equal to s prime of t. So the definite integral from time 1 to time 2 of the velocity function is equal to the position at time 2 minus the position at time 1, and that is the net change of the position or displacement of the particle from time 1 to time 2. The next bullet point says, if we want to calculate the distance the object travels during the time interval, we have to consider the intervals where the velocity is greater than or equal to 0, the particle moves to the right, and also the intervals when the velocity is less than or equal to 0, or when the particle moves to the left. In both cases, the distance is computed by integrating the absolute value of v of t. This should say computed. And the speed. So the absolute value of the velocity is the speed. Therefore, the definite integral from time 1 to time 2 of the speed function, or the absolute value of the velocity, dt, is equal to the total distance traveled. Below we see how both displacement and distance traveled can be interpreted in terms of area under a velocity curve. So we have some velocity curve here, and our horizontal axis is time, and our vertical axis is measuring the velocity. So the displacement is equal to the definite integral from time 1 to time 2 of v of t dt, which is the same thing as area 1 minus area 2 plus area 3. So that's essentially the net area in that case. And the total distance traveled is equal to the definite integral from time 1 to time 2 of the absolute value of the velocity function dt, which is equal to a1 plus a2 plus a3. So if you don't remember, the way that the absolute value works when you take it of a function is, if you have a function that has some parts of it that are below the x-axis, if you take the absolute value of v of t, then everything that's below the x-axis essentially gets reflected so that it's above the x-axis. And so another way that you can think about it is, notice that this is a plus instead of a minus. So that's what we are looking at if we want the total distance traveled. The acceleration of an object is a of t, which is equal to the first derivative of the velocity function, or v prime of t. So the definite integral from time 1 to time 2 of the acceleration function dt is equal to the velocity function evaluated at time 2 minus the velocity function evaluated at time 1. And this is the change in velocity from time 1 to time 2. Example 5 says, the velocity function in meters per second is given for a particle moving along a line. Part A says find the displacement, and part B says find the distance traveled by the particle during the given time interval. So our velocity function is v of t equals t squared minus 2t minus 3, and we're looking at this function over the interval from 2 to 4. And our velocity function is a quadratic function. Let's go ahead and do part A first, which asks us to find the displacement. And we saw the formula for up above. I'll just go ahead and copy it down again. So it's the definite integral from time 1 to time 2 of our velocity function. So in this case, our time 1 is 2 seconds, and our time 2 is 4 seconds. And then our velocity function is t squared minus 2t minus 3 times dt. So I'm going to go ahead and use the power rule. I'm going to increase my power by 1, divide by that new power. Same thing for the next term. And I want to evaluate this expression from t equals 2 seconds to t equals 4 seconds. So let's go ahead and plug those in. All right, I went ahead and plugged in t equals 2 and t equals 4, and this is what I got. And our final answer is 2/3 when we simplify this expression. And our units for this is that our displacement is 2/3 meters. So that is our final answer for part A. So for part B, we want to calculate the distance traveled, which is equal to the definite integral from time 1 to time 2 of the absolute value of the velocity function, which I've copied down here. Because our velocity function is a quadratic function, if I were to sketch a graph of it, it would be an upward facing parabola. And I'm going to go ahead and factor that. So we have t squared minus 2t minus 3. That factors into t minus 3 times t plus 1. And if I set that equal to 0, and I use the zero product principle, I get t minus 3 is equal to 0, and t plus 1 is equal to 0. If I solve both of these for t, I get t equals 3 and t equals -1. I'm not really concerned with negative values of time, but the reason that I'm doing this is because if this was my velocity axis and this was my time axis, I know that at -1 it crosses the t-axis, and at +3 it crosses the t-axis, and so maybe my graph looks something like that. And if we're taking the absolute value, essentially what's happening is anything below the t-axis is getting reflected so that everything is positive or above the x-axis. Now, we're really only concerned about this function between time 2 and time 4. So to answer this question, I want this area and I want that area. Now, how do we get that when we have an absolute value bar here? So one way of going about doing this is I can take my definite integral that I have right here with the absolute value bars, and I can break this up into two definite integrals. So my first one would be the definite integral from time 2 to time 3, and I'm going to include my velocity function. Now, that's the original velocity function, but between time 2 and time 3, the output values are negative. So to get that to reflect over the t-axis, I need to throw a negative sign in front of that. And then my second definite integral, I'm going to add on the area underneath the curve between 3 and 4, and that one's just going to be for my original velocity function. And now we can go ahead and calculate these. So I have this is equal to negative t cubed over 3 minus t squared minus 3t, and I am evaluating that between t equals 2 and t equals 3, and then plus, that's going to be the same expression inside my brackets. And now I'm evaluating this one between t equals 3 and t equals 4. All right, so I went ahead and I plugged in those numbers and did some arithmetic, and I ended up here, and now I have -1 times the quantity 1 minus 8/3 plus 64/3 minus 19, and if you simplify that, you should end up getting that the total distance traveled is 4 meters. And that concludes this example.